Good morning, everyone. I hope everyone's weather is as nice as it is out here in California. We're having an absolutely beautiful day here. Today we have Dr. Jeffrey Strickland that will be talking about discrete event simulation using ExtendSim, focusing on output analysis. And Dr. Strickland served in the United States Army in numerous tactical, operational, teaching, and research assignments. He's worked with NASA and a variety of defense industry contractors. He holds a PhD in mathematics and an MS in mathematics and is a certified simulation and modeling professional. He's authored the book Discrete Event Simulation with ExtendSim 8, and I'm looking forward to his talk. With that, I'll turn it over to Dr. Strickland.
Okay, welcome everybody. I want to thank you for attending today. As Dave said, this is going to be focused on output analysis. I did use ExtendSim for this particular presentation. I've used other software to do very similar analysis, so it's pretty tried and true. You know, I wish we had all day to talk about output analysis because there's really quite a bit to talk about, but we don't have that much time. So we're going to do some shortcuts and some parts that will be kind of like the details are left to the reader. But we're going to have a model that's simple enough that we can talk about in 50 minutes or 60 minutes. And we're going to do some pretty detailed analysis, or look at some detailed analysis. We won't look at all the details of the analysis, but we will talk about what kind of details in general we experience. And in particular, we're going to be looking at the initial transient period and the problems associated with autocorrelation when you do a discrete event simulation. And then we're going to learn about some experimental designs and some techniques that can help us reduce the impacts of these phenomenon when we're performing a discrete event simulation. So this is not the simulation we're going to look at, but this is a kind of a typical discrete event simulation where you have your model boundary, you have a set of state variables. And this particular one perhaps represents a combat model where you have position, fuel, size, health, strength, weapons, and so forth. You have some time advance mechanism. You have some external input events that are represented by physical models. You may have a model for moving, and then you may have a model for some direct fire combat, for example, or indirect fire combat where some explosion occurs. You have an external transition function that gets you into the state model that you're concerned with, and some internal transition function that changes the state of the system that is being acted upon. And then once that happens, you have some output generators that give you some output events, and it might, in the case of a tank unit on the move, gets indirect fire. They go into the model, their state changes, and what comes out perhaps is a different location, different appearance. Maybe there's some burning vehicles. The health has been reduced, the combat strength has been reduced, and so on. And then the formal model for this, if you're interested, is given in Ziegler, I think. Get a reference at the end. You can look at the references later. But the model that we're going to deal with is much simpler. It's just going to be an MM1Q, a single server, single queue, which is very easy to model in ExtendSim. We have an executive, which is the time advance mechanism. Every discrete event model is going to have one of those. We have a creator that is going to create entities, in this case arrivals. We have a queue where if there is something in the service process, the queue will hold the other entities until the service process is released. We have an activity which represents the service process, and then we have an exit which represents a departure from the boundaries of the system. We also have a couple of other tools in here. We have a plotter that will give us plots, and a statistical accumulator that will show us some statistics, means, standard deviations, confidence intervals, and so forth. So I actually ran this model, ran it at for 480 minutes. That's about a day's work in a like a bank or some other service for one run. And what I found in this particular run, if I had done another run separate from this run, I would have gotten a different answer. But the wait time was 2.2812. I know from queuing theory, because I can actually, for an MM1Q, calculate analytically the waiting time for this particular model, and that turns out to be 1.633. And so there's a difference between the average weight produced by the simulation run and the known mean of 1.633. You can also see in the graph below, and this was produced by the plotter in the model, that there is some spikes in the graph, and if you look at them carefully, that long waiting times for a prior entity is going to affect the waiting times for subsequent entities. Okay, so we have a case where autocorrelation is occurring in this model. So we have, a pretty good difference in the means waiting time or average waiting times, and some autocorrelation going on. So we're just going to explore our experimental design for a moment, and we're going to look at the validity of our model output. And there's a few reasons why we need to do this. First of all, simulation models do not necessarily start out in the steady state. In fact, most of the time we start a simulation model in an empty idle state because we don't really know for the phenomenon that we're dealing with what the actual steady state is. A lot of times our models are experimental. They're pre-development models that are driving development of system or so forth, and we really don't know what that steady state is at that point. Now later on, when we're looking at models that are testing the system that we've fielded, then we may know a little bit more about the steady state. The other thing that we have to look at is that standard statistical techniques can't be used typically with simulation model results. We have to resort to something a little bit more intricate when it comes to statistics and statistical analysis. And then really kind of a big point is the experimental design is as important as the build of the model. Of course, we need to get a valid model. We need to verify it, make sure that we've built the model correctly, that we've built the right model. But the experimental design and the discrete event simulation is just as important as those other things. So we need to look at some characteristics of queuing systems. This is just probably a review for many of you. We have an arrival rate. And for the MM1Q, that's a Poisson random variable, which looks a lot like that. And we say that lambda is the arrival rate, or 5 entities per hour, 20 entities per minute, whatever the case may be, for the arrival rate. We have a service process, amount of time it takes for a customer or an entity to receive a service, and in a weird sort of way you can think about the time it takes for a combat vehicle to be engaged by artillery, if you want to consider that a service. Service times are described by an exponential random variable, which looks a lot like that. And we typically use mu as the service rate. And then the average service time is calculated by 1 over mu. So in this particular model, what I used was a inter-arrival time of 0.7 units and a mean service time of 1.0 units. Now what this will ensure is that this model is a stable model, because the service time is going to be well, the ratio I'll have to say between the service time and the arrival time is going to help us have a stable model. Now, with this particular model, as I mentioned before, we know what the analytical solution is, and that should be appearing on the screen now. And if we calculate that, as I previously stated, it's 1.63333, and so on. So that ratio that I was talking about earlier is 70% over the long period. And because the system, or rather because the arrival rate is less than the service rate, we're going to have a stable system. So what I've done in advance is I did some analysis, and a particular analysis I did was 20 independent replications of the model consisting of 500 observations each. And in each replication, the initial waiting time was set to 0, indicating the system started in the empty idle state. And then on the next slide, I'll show you a graph that shows the average over 20 replications of each observation in the series. And got a little bit of a time delay here. There we go. There's the graph, and the red graph is the actual run. The blue or the black is kind of the moving average there. But you see that when we start out in the empty idle state at 0, it jumps up quickly to, I don't know, about 1.5, maybe 1.6, and then jumps around a lot all over the place and doesn't really look like there's any steady state being reached within that 500 interval, 0 to 500 interval. So what is causing our problems? So influences on the mean. We have the initial transient period, which I've mentioned before, and we'll talk about that next. And we have autocorrelated observations, which I mentioned before, and we'll talk about now. And what happens, and I kind of alluded to this, is that the waiting times are not independent. Okay, they're autocorrelated in this simulation. So in other words, if a customer's waiting time is small, then the next customer's waiting time is small. And if a customer's waiting time is a long time, then that affects the waiting time of the subsequent customers being long as well. And then the previous graph shows this effect. So the practical effect of this behavior is that the ordinary statistical methods that we use in, data analysis in general cannot be applied naively to compute the statistics, and in particular the confidence interval of the mean for the output of a discrete event simulation. But when appropriate techniques are used, we can get good results, but we're going to need a lot of data usually in order to do that. Okay, initial and transient period. Okay, there's a warm-up period during which the mean waiting time appears to increase to a value. In this case, it was close to 2, and then should settle back down to where we know the average waiting time for that MM1Q, given the inter-arrival time of 0.7 and the service time of 1.0. So if we were to look at the first 100 observations, there would, and I don't have the graph showing here, but there would be enough evidence to show that within that, after that first 100 observations, that we are probably beginning to see steady state behavior. Now, if we looked at the actual stationary distribution waiting time of the MM1Q, it would look something like that. And if the first waiting time is chosen from this distribution, then all the subsequent waiting times will be from this distribution as well. And by generating the first waiting time, we can produce a sequence of waiting times, all of which are from the same distribution, which the bottom graph on the next chart is going to show. There's a little bit of delay here still. If you look at the bottom graph, now this is still simulation, so there's some jumping around a bit, but if you look at the moving average, the dark line in the middle, we're starting out pretty much near steady state. It's about 1.5, 1.6, and then it stays along kind of an ugly line throughout the simulation for a period 0 to 500. If we look at the top one, this is not starting out in the steady state. We start out with the empty service, empty queue, or the empty idle condition. And the graph increases initially up to, the first spike is around 2.0. It goes down, it goes back to 2.0, goes down, it goes back to 2.0, and so on. And even all the way out to 500 in this particular one, we have not reached steady state, just by a comparison of the graphs. So the initial transient behavior, or the warm-up period, is an important characteristics of observations from a discrete event simulation. In every simulation of a dynamic system that we implement is going to begin in some fixed state, whether or not that is the empty idle state, the steady state, or our best guess of what the steady state might be. It's going to start in some fixed state. Typically, however, the initial state cannot be selected from the stationary distribution, which I've alluded to before, because we don't know necessarily what that distribution looks like for the simulation that we wish to run, or for the system that we wish to simulate. And then every simulation of a dynamic system must go through this warm-up period or initial transient period before exhibiting the behavior of its stationary distribution. So after the initial transient period, we assume that all the remaining observations are sampled from the steady state. The problem is actually determining when is the initial transient period over. So how long do we need to run the simulation in order to determine that? And there are several techniques to do that. A very easy technique with the technology we have available to us today is do a graph and look at it graphically. I know the graph on this chart, you see an initial spike. The times are arbitrary. In fact, they don't even show up very well at the bottom, but the times are arbitrary, and after about 1, 2, 3, 4 or so units, time units, this particular simulation looks like it has achieved steady state. So the next problem is to choose a method to compute the confidence interval for the mean once it has reached steady state. And the simplest method to do this is called the batch means method, or the method of batch means. And this method is actually indicated graphically here, where we group the observations into several batches, and then we compute the sample means of each observation in the batch. And I don't know if you can see the straight lines, but between each of those dotted vertical lines, there's a horizontal solid line that is supposed to represent the average within that interval or within that batch. And then once we do that, we are going to take those averages and compute a grand average and use that to compute a confidence interval. So just kind of a computational example, we have a series of observations. We divide them into batches. We calculate the mean of each batch in a normal manner. Then we take those observations, or those means, and we compute a grand mean, and I'll call it a grand standard deviation for the entire run. Then we use that in the normal method of calculating the confidence interval. And this one represents a 95% confidence interval. And then there's some guidelines about batches and batch sizes, and how many batches, how many observations within a batch, and so forth. And if we select a sufficiently large, which is a relative term, and there's some techniques to determine how large a batch should be. But if we have one sufficiently large, then we're going to be pretty much guaranteed that the means are going to be approximately normally distributed, so that we can do this standard method of calculating a confidence interval using the grand mean of those batched means. And then the batched means will be approximately independent when the batch size is sufficiently large as well. And our objective is to select a batch size large enough that the batch means are approximately uncorrelated. And then at the same time, we have to make sure that we have enough batches, or the right number of batches formed in order to ensure that the batch means, or not the batch means, but the means from the separate batches will be approximately normally distributed as well. And this is a kind of a rule of thumb. Like I said, there are techniques, mathematical techniques, in order to determine, appropriate batch sizes and so forth. But the rule of thumb is at least 10 batches with a batch size of at least 100 observations. So 10, 100. Now, an alternative to the batch means method is to run several independent replications of the simulation. And for each replication, we compute a sample mean, and then we use these sample means to compute a confidence interval for the mean. Since each replication that we run for the simulation starts in the same initial condition, we're going to be guaranteed that the sample means are mutually independent and not just approximately uncorrelated. So there's an advantage of doing this alternative means, of doing multiple runs of independent replications. However, each replication, or each run, still has to go through the initial transient period, and each one of them must still reach their steady state. And typically, nowadays anyway, we use graphical method such as time series plot to judge the adequacy of the initial transient period. So this is kind of a relook at that design of experiments with 480 minutes, one run. We didn't see that the waiting time of the queue does not appear to have reached the steady state. The average waiting time, which we know analytically is 1.6333 repeating, is different. And then we can see on the graph to the left that the waiting times are autocorrelated. So this DOE does not produce the results that we were looking for. Now, if we were naive, our first thought might be, well, something's wrong with our model. But in reality, something is wrong with our experimental design. And it has to do with those effects and the methods of fixing those effects that we talked about: the initial transient period, warm-up period, and the autocorrelated observations. Now, if I take a design of experiments, do it for 660 minutes, and I'm hoping, because I haven't I haven't shown you the graph yet. I'm hoping that by doing it 660 minutes, I'm going to cut off a bit of that initial transient period. I'm going to do 10 replications. And when I do that, if you look at my highlighted confidence interval down there, it's 1.620 plus or minus 0.2712, and the actual mean of 1.6333 falls within that confidence interval. Okay, now this is not necessarily the best I can do, but this is not a bad experimental design. 660 minutes, 10 runs. Now here is what is going on. This is the graph I had not shown you yet. When we have multiple replications. Okay, each replication is not going to be the same, but they're all going to go through an initial transient period, which you see there at the beginning. And in fact, this particular set of replications probably do not reach steady state until somewhere around the time of, I don't know, maybe 1100, 1150, down toward the right end of the graph. And I just I've put some solid horizontal lines there where I think it might have reached steady state, and I started calculating just graphically, no numbers here. I'm letting that represent the means for the steady state of the simulation for those 3 replications, with the first part of that being cut out as being the initial transient period and not calculating the statistics for that initial transient period. Now, most simulation tools, and ExtendSim does this, it gives you the means for telling your statistical accumulator to not count the statistics up through a certain time or up through a certain number of observations, which you've predetermined through analysis is the initial transient period. And then it will collect, and if you choose batch, observations beyond that initial transient period. So here's a design of experiments with 720-minute runs, 100 runs, and I've actually initialized it with 2 entities. And I can do that with the create block in ExtendSim by just a simple click of a button. And this is going to have an effect on the initial transient period because it's going to put us somewhere near steady state to begin with. And then I've increased the batches or the number of replications to 100, which is in some sense in increasing the batches because I can look at each run as being a batch, like I said, in some sense. As I stated, it doesn't start out empty idle. It starts out with 2. Now my confidence interval is getting a little bit narrower, and it's 1.626 plus or minus 0.0849, and our true mean of 1.6333 repeating lies within that confidence interval. Keeping in mind that I've pretty much, although I haven't looked at it graphically, pretty much eliminated the initial transient period because I'm starting out near what I think the steady state is. So, quick summary. First of all, DES is only one kind of dynamic simulation that you can perform in ExtendSim. ExtendSim is a quite versatile tool, but it's a good tool for running discrete event simulation. Discrete event simulation is estimated stochastic, dynamic and discrete model outputs, a DES scheme for modeling a system as it evolves over time by representation in which state variables change instantaneously at separate points in time, as opposed to a discrete time model where we're looking at state changes within set time intervals. So in the DES model, we're just looking at, as the states change, we're going to examine that time that the state changed. When simulating a dynamic system with DES, we may encounter two issues, and we usually do encounter those two issues. Easy to see with the MM1Q model, and easy to analyze with the MM1Q model because we know what it should look like, and those are autocorrelation and warm-up periods. But if we can deal with those in the MM1Q model, then any model that we have that's has multiple queues, multiple services, then we can be confident that our methods, of our design of experience and the methods that we used within those design of experience will work on those models as well. And I've done some pretty extensive models with ExtendSim to include the reliability and launch availability of the NASA Ares 1 crew launch vehicle, which was the crew launch vehicle that would replace the shuttle program. We actually had a successful test flight in that before the program was canceled for other reasons than failure of the program. Successful program canceled to pretty much privatize space. So the design of experiment that we choose is going to have a major impact on the accuracy or the validity of the outcome. On the NASA model that I mentioned, it was, like I said, it was a quite extensive ExtendSim model. We actually ran that model for several days to get enough observations and enough replications in order to ensure that we had independent runs, no autocorrelation, and that we could perform the proper statistical analysis to develop good confidence intervals for the mean. And we can settle these issues, as I stated, by using batched means or as an alternative replication of runs. And in both cases, really, we need long run times. Obviously, with the batch means method, if we're just doing one run, we're going to need an extremely long run time to get our rule of thumb, 10 batches, 100 observations. And although we still need long runs with the replication method, they don't have to be quite as long because we're doing independent runs of each replication. So that's the summary. I think my last slide is a list of references. I referred to Ziegler on there. He's the bottom reference. Law and Kelton is where the batch means method was referenced from. And somewhere in there, second from the bottom, is my book, Discrete Event Simulation Using ExtendSim 8. And so I think I've left us sufficient time for some discussion, if there is any.
Thank you, Dr. Strickland. I don't see any questions up, but please ask your questions. I have a comment about this. One area of research that I've noticed going on is researchers trying to develop automated systems for determining when the system gets to steady state. And as far as it applies to generalizing it for any kind of model, that really hasn't been that successful. I went to a presentation at last year's Winter Simulation Conference where they basically said, you know, we've kind of figured out how we could approach this, but when you really try to generalize it, it wasn't all that feasible, which I thought was interesting. That there's still kind of this very soft part of simulation where you can't you can't automate something, you can't computerize it. There's still the human in the loop is still very much required. I'm sorry, go ahead.
You know, particularly with more complex models, the more complex the processes are, the more difficult it is to determine what that initial transient period is. If you take the NASA model, for example, that crew launch vehicle, which affects the reliability and the launch availability, is not, you know, just sitting in place ready at Cape Canaveral for launch. It's being assembled in several locations. The solid rocket boosters, the first stage, second stage, the engine, the various components that make up those larger three components are being made all over the country, are being shipped to Cape Canaveral, being assembled in the vehicle assembly building. I don't know if you've seen that big, huge building down at Cape Canaveral where they put this stuff together, and then being moved out on a movable launch pad to be launched. So there's some very complex issues there that are being modeled, and consequently not really any good way other than experience with that type of program to determine when you've reached steady state.
We got some questions here. Dan Houston is asking, you showed two plots, the first from the initial model and the second showing stationary behavior. I did not catch what you did in the model to produce the stationary plot.
In the stationary plot, what I did was I started out with, it is a case where I started out with two entities. Rather than starting out in the empty idle position, I created two entities that are in the simulation at time 0. So okay, that puts me near steady state.
So you dump some items in at the beginning so that you're closer to. So you have to take a bit of a guess there to say, I think there's on the average 2 entities in the system, or at least you're closer to the average.
Yeah, that's an educated guess based on a lot of analysis of the MM1Q, because that was for the MM1Q. And that's just a simple matter of going to the create block and telling the create block to start out at time 0 with 2 in ExtendSim.
Here's a really good question. How do we think about predictions for systems that never reach steady state because operating shifts are never long enough?
Can you repeat the question?
Sure. Yeah, how do we think about predictions for systems that never reach steady state because operating shifts are never long enough? So I assume that the system might actually have different time periods where it's going to move from one steady state and then something changes. Yeah, okay. For example, my medical clinics work on 4-hour shifts and never reach steady state. So you'll have you're always in a transient state because, well, maybe not always, but you're moving from one steady state to another one.
Right, and you're actually working under different simulation assumptions. In that case, you're not working in a what's the correct term for that? You're not working in a stationary distribution.
Right.
So what you actually have is you have to look at different time periods. You can look at this in the same way as let's say peak times for use of an ATM. Typically, you might go by an ATM in the morning. I would use a bank, but people just don't go to the bank anymore. So you might go to the ATM on your way to work. It might be in a convenient location. It might even be at your workplace, and you go by the ATM, get some cash. Or you may be running late and coffee is more important, so you go get the coffee and you wait to go to the ATM at lunch when everybody else is going. Or maybe on the way home from work. So you got some spike times in there where the inter-arrival times are different than other times in the day. So you have different distributions that you're dealing with, and you have to look at those different time periods separately in a simulation.
Yeah, it goes back, at least if I can make a comment, to the purpose of the model. So sometimes we'll have people build models where you only look at one time period. So you just take one shift and then extend that out for a longer time, because your simulation model doesn't have to be an exact mimic of the real system. It's something that you're using to study the real system. So you could say, well, I want to look at my emergency room at the peak time of the day, and just take that peak time and extend it out for 48 hours. Even though that's not realistic, you can see kind of in a steady state view, can I handle that peak time with the resources that I have? Or maybe I'm sorry, go ahead.
No, you go ahead.
Oh, okay. Or maybe you want to study how you transition from one shift to another. So that would be a different kind of model. So it's easy to kind of, and I find myself doing this, kind of, okay, I'm going to build the model, I'm going to build it the way the system really operates. But maybe I want to take a level back in abstraction and say, I'm going to alter my model a little bit to get more information about the system that I can't get if I built it exactly how it operates. I'm sorry, Jeff, go ahead.
Certainly. We try to build models as accurately as we can. Typically, even though we try to achieve the accuracy, we just don't know enough about the phenomena that we're dealing with to model everything in it. There's a quote that I like to use that goes like this: all models are wrong, some models are useful.
Yeah.
I think George Bach said that. I can't remember for sure, but it's true. I mean, we don't capture everything in our models. One thing that we don't capture well at all is human behavior in the models, and often we leave that out or account for it with some other means.
Another question is, did you change the random number seeds for multiple replication runs?
No, I did not. They have the same random number seeds.
They do. I would have
Yes.
expected those would have.
Wait a minute. No, I'm sorry. I did change the random number seeds in this one.
Okay.
I actually performed an analysis where I did not change the random number seeds.
If you don't change the seeds, you should get identical results in each.
And
each
right,
run.
and you get identical results.
Yeah.
And I was looking. What I was looking at was extremely long runs, and what was the how good. It was really a matter of how good was the random number generator. It wasn't so much about how good was the simulation. It was a completely different study. In the book, I talk a little bit about random number generation, but I did actually a lot of work on random number generation. I actually used ExtendSim one time to do that, and I was looking at the quality of random number generation. I looked at ExtendSim, I looked at Arena, I looked at Excel. Excel actually, between the time I looked at it and today, actually improved their random number generator. But ExtendSim's random number generator I found to be very good in terms of simulation random number generators.
Let's see, another question here is, near the beginning of this is Ken Cruz, near the beginning of the presentation, a decision was required to determine if the model was in error or the design. Could you expand upon the explanation a bit? Sorry.
Okay, so was the model wrong or was the design wrong? Is that the question?
I guess so. I'm not sure. Required.
Okay.
Oh, go ahead.
The model is correct. The model is so simple. I mean, there's not much going on in the model at all. You've got an arrival process where you create your entities. You have a service process where they are going to receive service. And then you have to have somewhere for them to wait. That's your queue if they're not receiving service. And then once they leave the service, instantaneously they're out of the bounds of the model. So it's a very simple model. We know what the model's behavior is analytically. We know, we just put in the inter-arrival times and service times, and really it's kind of it's almost a no-brainer. There's nothing more I could do to the model to make it better, other than the simulation setup, the experimental design, and as I mentioned in one spot, I put in instead of starting in an empty idle position, put in 2 entities to start near steady state, because I had a little bit of understanding of when the system would reach steady state after many trials. So it was really the design, and as I improved the design, but to account for those problems, the initial transient period and autocorrelation, as I improved the design of the experiment to eliminate those problems, the simulation performed like the analytic model would.
Okay, yeah, and I got a clarification. Yeah, that was the question. Ken, I think that's a whole nother webinar. In fact, maybe that's a good topic. I should try to find someone that could talk about that as model validation verification, really making sure that you've got what you think you've modeled. And of course, in the simple model, that's the MM1Q is a great model for illustrating all sorts of simulation concepts, but I'm not sure validation verification is one of them.
Not really. I mean, that one. I think we could say pretty much that's very easy to verify and validate. And I really think of 2 things when I think. And I actually worked as a technical director for 2 years for V&V for Missile Defense Agency, and I always spoke of verification and validation. Verification being, did we build the model correctly, and then validation, did we build the correct model? Did we build the model that the customer was expecting us to build? So one is kind of a coding thing, and one is kind of is sort of a, did we really understand what we were supposed to build in the first place?
And depending upon how important the model is, there's different techniques. Yeah, there's a whole. We could go on and on about this. We've got a few more questions here, and we're running a little short on time, so let's move on. But Ken, that's a great topic for a future one. Gray McQuarrie asks, how would you use the clear statistics, if at all, in a simulation like this? For example, would you clear the Q block, which would seem to me to defeat using this to get to a steady state? Let me repeat that one more time. How would you use the clear statistics, if at all, in a simulation like this? For example, would you clear the Q block, which would seem to me to defeat using this to get to steady state?
No, not necessarily. If you in fact, the technique that one of the techniques that I used, and I didn't really talk about in the presentation. It is talked about in the book, where I did use the clear statistics block, but what I'm using it for is clearing the statistics after it has reached the initial transient period. So I say after a certain time, because I've already analyzed what that certain time might be. I say after a certain time, clear statistics, start over, run it for an additional, I may make my run, say I make my run 1,000, I don't know, let's just say minutes, 1,000 minutes, and this is the hypothetical situation. My first 500 minutes is the initial transient period. And I've determined that some way, analytically or observationally or experience or something. Then I clear statistics after that first 50 minutes, and then start accumulating statistics after that for the second 500 minutes. And then I do multiple replications, and I do that for each replication. I'm going to get better results that way, at least in regards to the initial transient period. The only other way that I'm going to get good results is having some idea what steady state is, and put some entities in that create unit rather than starting at the idle state.
There's some other comments here, but I think they're mostly follow-ups, except for one other, which is, do you make the models used in your book available online or on a CD?
They're online. They're at my website.
Okay. Okay, and then, yeah, Ken Cruz has a comment here that says, I believe he used math approach to determine an answer. Yeah, that's one of the big advantages of looking at the MM1Q is that you can fairly easily derive, using queuing theory, a theoretical answer. So that allows you to wrap everything up in terms of validating the model. That
right.
You know you've got the right answer because you've got a theoretical approach. But of course, if we could do that with every simulation model, nobody'd build any simulation models because you just go to queuing theory right away.
And really, the MM1Q, and I think there may be 2 or 3 queuing models. And if you know anything about queuing models, they can get quite complex. There's only about 2 or 3 that we have analytical solutions for. And beyond that, we're hosed.
Yeah, and that's the reason we use simulation is it's a tool of last resort. You use something else if you can, because simulation tends to be kind of messy. Linear programming or decision theory or queuing theory, but unfortunately it solves the greatest range of problems. So it is a tool that's probably the most useful of the operations techniques, particularly when applied to queuing systems. So it looks like we're just about out of time. Thank you very much for all the good questions, everyone, and Dr. Strickland for taking time out of your schedule to present this.
Dave, thank you very much, too, for inviting me to do this.
Oh, yeah, we appreciate it. Thank you again. I'm going to end the session now.